Good evening, friends. Welcome to second session. If you didn't watch first session, I am giving a link in description box. Please, you can tap the description box first session link and you can watch first session video also. Okay. Here, now we'll take basic nature of aliphatic amines. So first, you should know about amine. Amine means how we can expect basic nature of amines. Amines are nothing but NH2 group containing compounds. They are obtained by ammonia. They are obtained by ammonia. Here on this nitrogen there is a lone pair of electron. All amines act as Lewis bases. All amines act as Lewis bases. See here, if it donates this nitrogen, the electron pair which is present on nitrogen, when donated to other substances, then we can say it is Lewis base. Lewis base means the compound which can able to donate electron pair to other substances is nothing but Lewis base. This basic nature again depends on inductive effect. See here, if you write R group, R is nothing but any alkyl group. We can write any alkyl group. You know, alkyl groups have plus I nature. Alkyl groups have plus I nature. Therefore, all the electrons which are present in sigma bond are attracted towards the NH2 group. So, on nitrogen, electron density increases so that it has more availability of electrons. Therefore, it can easily donate those electrons to other substances so that it acts as strong base. So here based on this what we can write plus I group, otherwise we can write ERG. ERG means electron releasing group is directly proportional to basic nature. Basic nature. Similarly, whenever NH2 is amine, here CH2 Cl hybriding. This is chloromethyl group. This is directly methyl group or alkyl group. See, chlorine is minus A group. You know, chlorine is minus A group, so that it can attract these electrons towards itself, so that this carbon again takes electrons from nitrogen. So, because of electrons are moving away from the group, so that on nitrogen availability of electrons decreases. Here, availability of electrons increases on nitrogen because of this alkyl group plus I effect. Because of chlorine's minus I effect, here availability of electrons decreases on nitrogen. If availability of electrons decreases on nitrogen, it is unable to donate this electron pair to other substances, so that basic strength decreases. Therefore, what we can write here, minus I nature, otherwise minus I nature are called as EWG, electron withdrawing nature. So, is inversely proportional to basic nature. Basic nature of aliphatic amines. Basic nature of aliphatic amines. When EWG, otherwise minus I nature increases. When minus I nature increases, basic nature decreases. So this you have to remember. Here CH3NH2, and I am giving one more example for this. CH3NH2 and NH3. Ammonia also Lewis base. Ammonia also Lewis base, because here there is a lone pair of electron. Methyl amine also Lewis base. Here because of this lone pair of electron, all amines, otherwise all the compounds which contain lone pair of electrons on central atom can donate their electron pairs to other substances, so that they act as Lewis bases. Here only hydrogens are there. In ammonia only hydrogens are there, so that there is no I effect. There is no I effect in ammonia, but there is a plus I effect in methylamine. Here there is a plus I effect. Methyl group has a plus I nature. These electrons are shifted to nitrogen. Here there is no plus I nature. So that here the electron density, here electron density increases. Electron density increases on nitrogen. Therefore, basic nature increases. Basic nature increases from ammonia to methylamine. So this is how plus I effect affected on basic nature of amines. Then in particularly only gaseous medium, otherwise non-aqueous medium, we have different amines. So basic nature of amines, primary, secondary, tertiary, and ammonia. Amines in gas phase, or non-aqueous phase, non-aqueous phase. Here in water phase, in aqueous phase, basic nature of amines are different. In amines chapter in second year, we will discuss clearly. Here only gas phase I am considering. Otherwise only non-aqueous phase I am considering. See here what is non-aqueous phase? CH3, N, CH3, here CH3. Here there is a lone pair of electron. This is tertiary amine, we can say. This is tertiary amine. Then CH3, here NH, then here CH3. There is a lone pair of electron on nitrogen. This is secondary amine. This is a secondary amine. Then CH3, NH2. CH3, NH2. Here also there is a lone pair of electron on nitrogen. This is the primary amine. And lastly, ammonia. NH3. There is a lone pair of electron. So, what is the order of basic nature of these compounds? See here on which nitrogen availability of electrons are more, on which nitrogen electron density is more, that nitrogen can able to donate more and more electrons to other substances. So that is having more basic nature. So here these three methyl groups can donate their sigma electrons to nitrogen. So that here the availability of electrons on nitrogen increases, so that it can easily donate its electron pair to other atom in gas phase, otherwise non-aqueous. This is very important. This order is not for aqueous medium. Then same thing, secondary. Here primary, then ammonia. This is the order of basic nature of different amines: tertiary amine, secondary amine, primary amine, and ammonia in non-aqueous medium or gas phase. Here, why it is so? Why basic nature decreases means plus psi nature gradually decreases. Plus psi nature decreases from tertiary amine to ammonia. So this is about inductive effect and their applications. Then next one is electromagnetic effect. Next one is the electromagnetic effect. Next polar effect is electromagnetic effect. We will discuss about it. Electromagnetic effect is temporary effect. Electromagnetic effect is temporary effect. Second polar effect is electromagnetic effect. Electromagnetic effect, otherwise we can say E effect. E effect. So here I am writing first conditions. So it requires 5 electrons. It requires 5 electrons first. That means it requires a multiple bonded compound. Multiple bonded compounds are required. Then second thing is it is only in the presence of attacking reagent. It occurs or it takes place only in the presence of attacking reagent. It is only in the presence of attacking reagent. That means if you remove attacking reagent, what happens? If you remove attacking reagent, if you remove the attacking reagent, the molecule, otherwise the bonds which are displaced again takes the original position. Means molecule reverts to its original position. Its original position. That means it occurs only in the presence of attacking reagent. So that this is called as temporary effect. It is called as temporary effect. Temporary effect. If you remove the attacking reagent, again the bonds which are delocalized or displaced or moved to other atom, no, those electrons or the bonds again takes their original position. They retains their original state. So molecule reverts to original position, so that it is temporary effect. But here the complete charges are formed, not like inductive effect. In inductive effect, you observe partial positive charge, partial negative charge. But here complete charge, complete charges are obtained. Complete charges are obtained. So that this is strong. This is strong compared to I effect. Compared to inductive effect, it is strong. So whenever both the effects, E effect and I effect, whenever both the effects are simultaneously occur in the molecule, whenever E effect and I effect both are simultaneously present in the same molecule, E effect predominates because it is strong. E effect predominates. This you have to remember. That means this is strong. E effect is strong. I effect is weak. If both effects, electromagnetic effect and inductive effect, both are present in the same molecule, both are opposing, then which effect we can consider? We can consider E effect, but not I effect, because I effect is it is temporary, it is permanent, but because of partial charges, it is weak. Remember that. Here also we have different electromagnetic effects, plus E effect and minus E effect. Excuse me. Before that, I'll give the statement related to electromagnetic effect. Electromagnetic effect also one of the polar effects. So that here also polarity is produced in the molecule. Here I am writing about the electromagnetic effect statement or definition, like polarity is produced. Polarity is produced in the molecule. Polarity is produced in the molecule due to displacement of pi electrons present in multiple bonded compounds. Pi electrons present in multiple means more than one, multiple bonded compounds. Multiple bonded compounds in the sense, what are multiple bonded compounds? Maybe alkenes. You can say alkynes. Alkenes or alkynes or carbonyl compounds. Carbonyl compounds in which there is a double bond between carbon and oxygen. Aldehydes or ketones we can say. Then cyanides, etc. Cyanides means C triple bond N. C triple bond N. These are generally the compounds which contain multiple bonds. So here polarity produced in the molecule due to displacement of pi electrons present in the multiple bonded compounds. Displacement of pi electrons present in multiple bonded compounds to more electronegative atom. More En means electronegative atom from other atom. From other means which is less electronegative, and even it is in the presence of attacking reagent. This is important. The presence of attacking reagent. This is complete information. Here in this conditions also included. See, polarity produced in the molecule due to displacement of pi electrons present in the multiple bonded compounds. It may be unsaturated or like saturated compounds like cyanides or aldehydes or ketones, to more electronegative atom. The pi electrons are displaced towards which side? More electronegative atom from other. In the presence of attacking reagent is called as electromagnetic effect. One more time I am repeating. polarity is created, or polarity is induced, or polarity is produced in the molecule due to displacement of pi electrons which are present in the multiple bond. Displacement of pi electrons present in multiple bond to more electronegative atom from other atom in the presence of attaching reagent is called as electromagnetic effect. Here we have two effects. One is plus E effect, other one is minus E effect. Plus inductive effect, plus electromagnetic effect, minus electromagnetic effect. Now we will discuss about plus E effect and also minus E effect. First we will discuss about plus E effect. If you want to write, please pause the video and you can write. So afterwards you can see the next screen. See here plus E effect I am going to discuss now. First one is plus electromagnetic effect. Plus electromagnetic effect. Generally, in alkenes and alkynes, we can expect this. Unsaturated compounds. In unsaturated compounds, organic compounds. Unsaturated organic compounds, we can expect minus E, plus E effect. Not minus E, plus E. Unsaturated compounds. So here, see if I write the representation, you can able to understand. This is alkene. This is alkene. See here, I am writing H plus ion. H plus ion means it is electrophile. This is attacking reagent. This is attacking reagent. H plus is attacking reagent. See, this attacking reagent is coming towards this carbon means yeah, already it has positive charge. That means the carbon which accepts this H plus ion must be with negative charge. So that see this pi electron migration is towards this carbon. If then this carbon will take negative charge, this carbon will take positive charge. So that this reagent, this H plus ion again come to the same carbon atom. So here migration of attacking reagent, the direction of movement of attacking reagent and migration of pi electrons towards the same carbon, then we can say it is plus E effect. Plus E effect is nothing but when transfer of electrons takes place towards attacking reagent. Transfer of which electrons? Transfer of pi electrons takes place. Transfer of pi electrons takes place towards attacking reagent. Towards attacking reagent. It's called as plus E effect. Transfer of electrons, pi electrons takes place towards the attacking reagent is called as plus E effect. See here, these pi electrons are moving towards this carbon. Towards this carbon only, this attacking reagent is coming. So here finally what we get carbon, this bond becomes single bond, and here bond, here we can write hydrogen, and here it will get positive charge. So this is about plus E effect. In alkenes and alkynes we can expect the same. In alkenes and alkynes we can expect the same. And particularly here unsaturated compounds means examples if they ask. Addition of here common example what we can write for plus E effect, addition of H plus ion. Otherwise we can say electrophile. Addition of electrophile. Addition of electrophiles to unsaturated compounds. Otherwise alkenes or alkynes. These are the common examples for plus E effect. Then minus E effect. What is minus E effect? Minus E effect means as per the same definition here already written here, transfer of pi electrons takes place towards attacking reagent. Here what we can write? Transfer of pi electrons move away from the attacking reagent. Here transfer of pi electrons takes place. Transfer of pi electrons takes place away from the attacking reagent. Away from attacking reagent is called minus C effect. What is minus C effect? Transfer of like pi electrons takes place away from, move away from attacking reagent. So common examples for this are addition of, here also addition reactions. Generally in addition reactions only we have electromagnetic effect, not substitution reactions. The electromagnetic effect is applicable for which reactions? Addition reactions particularly. This you have to remember. So addition of nucleophile, Nu minus means nucleophile. Addition of nucleophile to aldehydes, ALD means aldehyde or ketone or cyanides. They are the common examples or general examples for minus E effect. Minus E effect. See here I am writing reaction way. See here C double bond O, like I am writing, this is aldehyde or ketone, we can say carbonyl compound. This is the carbonyl compound, may it is aldehyde or ketone. Aldehyde or ketone. Here I am writing X minus. X minus is nothing but nucleophile. Nucleophile. See here between carbon and oxygen there is a double bond. There are pi electrons between carbon and oxygen. You know carbon is less electronegative and oxygen is more electronegative. Because of more electronegativity, this oxygen can take electrons, pi electrons towards itself. These pi electrons move towards oxygen. So oxygen will take negative charge and carbon will take which charge? Positive charge. Therefore, this negative charge attacking reagent, this nucleophile is now we can say attacking reagent. This is attacking reagent. This attacking reagent is now moving towards which side? This carbon. See here, this migration of electrons, pi electrons, and migration of otherwise attacking reagent direction is towards this carbon. See, if you observe clearly here, pi electrons means transfer of pi electrons. Transfer of pi electrons is away from attacking reagent. Attacking reagent is coming towards this carbon, but pi electrons are moving towards other atom. So this is the plus minus E effect. Here we can write like this. Here O negative charge, and here we can write X. So this is about minus E effect. Sometimes here lines also they may give double bond carbon plus here like Cn minus. Cn minus. Cn minus is negative charge. For example, if this electron pair is shifted to this side, so this carbon will take which charge? Can take negative charge. This carbon take positive charge. So here this Cn minus is coming to this carbon. Even though it is alkene, based on the representation what they are given, we can say is it plus E effect or minus E effect. If electron pair, pi electron pair is moving away from attacking reagent, we can say minus E effect. We can say it is minus E effect. Here also you can observe, even though it is alkene, actually this is not the characteristic property of alkene. Even though if they mention like this representation in the question, then we can say it is minus E effect. This is example for minus E effect. Why it is so? See here, pi electrons are moving to this carbon and attacking reagent is moving towards other carbon. That indicates what? Pi electrons move away from the attacking reagent. Here, pi electrons move away from attacking reagent. Pi electrons move away from the attacking reagent. So from this we can say this expression, this reaction comes under minus E effect. So even though this is not the characteristic property of alkene, based on the representation we can say it is minus E effect. So this is about plus E effect and minus E effect. There are no applications for this, like inductive effect we have applications now. By using inductive effect we can expect reactivity, stability of carbocations, then acidic nature of carboxylic acid, and basic nature of amines, and dipole moment. That is, we can explain many properties of different compounds. But for inductive effect, because of it is temporary effect, it is temporary effect, so that there is no much applications for electromagnetic effect. This much is enough for electromagnetic effect. Then next concept here is about resonance effect or mesomeric effect. So to understand the mesomeric effect or resonance effect, first of all you should know what is resonance. Resonance concept also very important. All are the basics. So many second year concept you can understand by these polar effects. Here next thing here is resonance. Resonance. See, each and every molecule you can take any molecule you can take that molecule that molecule has some different properties. Molecule to molecule there is a variation in properties. If you take one molecule, that molecule may show different properties, maybe melting points, maybe boiling points, otherwise any chemical properties, reaction towards the hydrogen, reaction towards chlorine, reaction towards different properties, maybe chemical properties or physical properties. So different properties we have. So all the properties are not possible to explain by using one structure. All the properties of the molecule cannot be, or it is not possible to explain by using one structure. To explain some properties we need one structure. To explain other property we need other Lewis structure. So that writing more than one structure for given molecule to explain all the properties is nothing but resonance. So the structures are called as the canonical structures. Otherwise the structures are otherwise called as the contributing structures. These contributing structures or canonical structures have no real existence. No real existence. It is imaginary. And resonance hybrid has a real existence. See here anything. For example, here I am taking benzene ring. This is benzene. Like this you can write. So here what is the property as per a physical property? In benzene there is a single bond. If it is carbon-carbon single bond, there should be bond length of 154 picometers. There should be bond length of 154 picometers. And here you can observe double bond. So carbon-carbon double bond length also it is 134 picometers. 134 picometers. For benzene we can write one more structure. What is the other structure we can write? See, whenever this bond shifted here, this pi electron shifted toward this side, this pi electron shifted toward this side. So that we can write like this one more structure. So these two are called as resonance structure. Otherwise, we can say canonical structures. Canonical structures. These two are canonical structures. Otherwise, we can say contributing structures. Contributing structures. Otherwise, we can say simply resonance structures. Resonance structures. Resonance structures or canonical structures. These structures have no real existence. These have no real existence. These have no real existence. But for the both structures, we can write one more structure, that is resonance hybrid. Like this, we can write. So here, whenever this bond shifted here this single bond becomes double bond, and this double bond becomes single bond, and it comes here. Then this single bond becomes double bond. Like that, if you take these two resonance structures, they move. Means it can converted into this compound, and this structure may be converted into this compound. So here in between these two I written arrow, double arrow, which is nothing but representation for resonance, and this is called as resonance hybrid. It's called as resonance hybrid. But as per experimental findings, see, in benzene we don't have these bond lengths. 154 picometers bond length and 134 picometers bond length is not possible for benzene, because these single bonds and double bonds are interchanged frequently. So we can't get single bond or double bond. So we can't measure single bond length and double bond length. So this is the property. This property is explained on the basis of resonance hybrid. See here, if you write like this, so all the pi electrons rotate throughout the molecule. Therefore, here we can't get double bond or single bond. So that here, as per experimental findings, bond length between any two carbon atoms in benzene is 139 picometers. It is 139 picometers. So it is more than double bond length and less than single bond length. So to explain this property, this is a physical property. To explain this property, we need these two structures. So here resonance is nothing but writing the more than one structure, because by using one structure it is not possible to explain the properties. So here when all the properties, here I am writing, when all the properties, when all the properties of a molecule, when all the properties of the molecule cannot be shown, won't be shown by one structure, by one structure. So what we need then, there is a need of, then there is a need of more than one structure, more than one structure to explain the properties, to explain all the properties, to explain all these properties. So these structures are nothing but resonance structures, otherwise contributing structures or canonical structures which have no real existence, which has no real existence. So this is simply about resonance. Why? What is the resonance term, and why we should take resonance structures or canonical structures? We should know. So one more time I am repeating. Resonance concept or this phenomenon is related to more than one structure. Why there is a need of writing more than one Lewis dot structures? Because by using one structure it is not possible to explain all the properties. To explain one property it requires one molecule, one structure. To explain other property it requires one more structure. So these two structures to explain the different properties are nothing but canonical structures or contributing structures or resonance structures. The phenomenon involved in this is nothing but resonance. The phenomenon involved in this is resonance. So here we have one more term, that is resonance hybrid, resonance energy. Sorry, one more term is resonance energy, resonance energy. Resonance energy is directly proportional to stability of the molecule. Stability we can measure by resonance energy. More resonance energy means more stability. So this you have to remember. For benzene, this resonance energy is 36 kilocalories per mole. 36 kilocalories per mole. Otherwise, the same thing we can write it as 150.62. 150.62 kilojoules per mole. Kilojoules per mole. Benzene is more and more stable. Why it is so means its resonance energy is more. What is resonance energy then? See here we have two different canonical structures and we have one resonance hybrid. Resonance hybrid we can write like this. So the difference in the internal energies of resonance hybrid and one of the stable canonical structure is nothing but resonance energy. Here I am writing what is resonance energy. Simply resonance energy is nothing but resonance energy is equal to energy, internal energy. Otherwise, the energy of resonance hybrid, resonance hybrid, which has a real existence, minus energy. Here I am writing minus energy of one of the stable canonical structure, one of the stable canonical or resonance structure. So this is the resonance energy. The difference between internal energies of resonance hybrid and one of the stable canonical structures is nothing but resonance energy. Resonance energy is directly proportional to stability. Resonance energy of benzene, resonance energy of benzene is how much? 36 kilocalories per mole. Otherwise, if we convert it into kilojoules, it becomes 150.62 kilojoules per mole. This is about resonance. And here one more important thing is if you write more than one structure or more than two structures or three structures for a given molecule, more than two structures or three structures or four structures for a given molecule, which structure is more stable? How we can decide which structure is more stable? See, for that we have some statements which we have to remember. So during writing this resonance structures, otherwise in different canonical structures there is no change in position of atoms. So in resonance structures, no change in position of atoms. No change in position of atoms. Only change is due to only change is with respect to electrons, and total number of lone pair of electrons will not change in any canonical form. If you write one canonical form, so if you compare that canonical form with other canonical form, so in both the forms total number of electrons must be same, and total number of unpaired electrons or lone pair of electrons also must be same. If electrons are different, means that is not that particular structure, means that is not at all related to that molecule. So that is not correct resonance or canonical structure for that particular molecule. Okay. Then a structure is more stable. Structure, canonical structure is the more stable. More stable when, here conditions you have to remember. When first one is that must be with more covalent bonds. More, I'll give examples for this. Covalent bonds. More number of covalent bonds containing structure is more and more stable. And second thing is all the atoms must be with octet structure. Means see here two structures we write. One structure has more covalent bonds, other structure has less covalent bonds. Means which is more stable? More covalent bonds containing structure is more stable. And all the atoms must be with the octet structure. Means other structure, two structures if you write, in one structure all the atoms are having octet structure, that means around that particular atom 8 electrons are present. In other structure 8 electrons are not present around some atoms. Then that is the less stable structure. So that here the structure is more stable when the structure must be with more covalent bonds, or the structure, in that structure all the atoms must be with octet. And next thing is less separation of opposite charges. Less charge separation we can say. Less charge separation between opposite charges. Means if you have 4 carbons, so if two opposite charges are present on one end, say 2 carbons in one structure, two opposite charges are present on one end, fourth carbon in other structure, then which is more stable? The structure with less charge separation, means the structure in which opposite charges are present on adjacent carbon atoms is more stable than first and last carbon. So between opposite charges there is a less distance, otherwise less charge separation between opposite charges. Then next thing is in the given structures, more electronegative atom, more En atom, more electronegative atom must take negative charge, then only it is stable. If it is more electronegative atom and it takes positive charge, means it is not stable, because the more electronegative atoms will not accept positive charge. Electronegative atoms always takes negative charge. Electropositive atoms always takes positive charge. So that also I am writing. More electronegative atoms takes negative charge. More electropositive EP. More electropositive atoms must take positive charge. Then only the structure is more stable. Otherwise, the structure is not stable. And more dispersal of charge. Charge must be more dispersed. More dispersal of charge. The structure with more dispersal of charge is more stable than other. Then one more also you can write identical canonical structures are more stable. Identical canonical structures. Identical resonance structures are more stable. Canonical structures are more stable. So these you have to remember. These conditions has to get a more stable nature, has to get more stability for that particular structure. It must obey these conditions. Then only it is more stable. Otherwise, it is not stable. If you compare the structure with the other structure, these conditions it must follow. Any one condition also we can consider. See, here I am giving some examples here. First, I am taking CH3COO minus acetate ion I am taking. Acetate ion. We can write different structures for acetate ion. See, example, acetate ion. Acetate ion is nothing but CH3COO minus we can write. For the same, I am writing CH3 C double bond O an oxygen negative charge. Here two lone pair of electrons are present. Here also two lone pair of electrons are present. See, we can write whenever this bond shifted to this oxygen, it will come here. So we can get one resonance form like this: CH3 C here O minus, then double bond O. Here two electrons. Here also two electrons. So these two are identical. See here only one charge is present. One more condition also you can expect. You can write in the conditions. The other condition is only one charge, means no charge separation is there, means it is more stable compared to other forms, other structures. See here no charge separation, only one charge is present, only negative charge is present, and it is identical. Identical means here an oxygen negative charge, here also an oxygen negative charge. Non-identical means during transfer of electrons, if one atom, means oxygen atom, if take negative charge, next time that negative charge it transferred to carbon, means it is not identical. Identical nature means one charge must be present on similar atoms, means negative charge is here. After delocalization or shifting this electron pair, electron negative charge means nothing but negative charge is nothing but electron pair. Then whenever this electron pair shifted here, this electron pair move here, so that oxygen takes negative charge, here double bond. So they are more and more stable. And we can write one more thing here: CH3 here C. This bond when shifted here, it becomes a double bond O. Here already minus charge is there. Here O plus, because this electron is shifted from here to here. Two lone pair of electrons are present. But here on oxygen, if you can observe, more electronegativity containing oxygen carries positive charge. So that this is not stable. This is not stable. Because always while writing structures, more electronegative atom must be with the negative charge, more electropositive atom, otherwise less electronegative atom with positive charge. Then only it is stable. This is one example. Then other example I am taking acrolein. CH2 double bond CH CHO or C double bond OH. This is acrolein, otherwise propanol. Propene 1 2 3 propene, and it is aldehyde propanol or acrolein. This acrolein. For this we can write different resonance structures. See, whenever this bond shifted here by electron, it will shifted to oxygen. So here we can write CH2 single bond. This electron pair shifted from here to here so that this carbon gets positive charge. Then here CH, then double bond, here O minus, then here hydrogen. This is one form. Then one more form also we can write in reverse order. Reverse order means see here I am writing same thing CH2 double bond CH C double bond OH. So whenever this bond shifted here, this bond, this pi electron shifted here. So for this also same thing we can write CH2 here minus single bond CH double bond C here O plus then here hydrogen. So one, this is also one same form. The first structure, this is second structure, this is third structure. So which is more stable? What is the order of stability they ask? So this is more stable because more number of covalent bonds are present here. See here 1, 2, 3, 4, 5. Only in between carbon, hydrogen, I written, I counted these bonds here. So otherwise you can check pi bonds. Here 1, 2, 2 pi bonds are present here. Here only one pi bond is present. So number of covalent bonds are less there. So less covalent bonds. Less covalent bonds. Here more covalent bonds. More covalent bonds. More covalent bond means more stable. Less covalent bond means less stable. And here if you observe on oxygen positive charge. So more electronegative atom will not accept positive charge. So that it is the least stable. It is the least stable. If they ask order, what is the order? First is more and more stable than, second is more stable than third. So like this we have to expect. So like these options they give, first option, second option, third option. First option maybe like first is more than, third is more than second. Second option, first is greater than, second is greater than third. One more option, third is greater than, first is greater than second. Like this they may interchange the first, second, third. Here this is the correct one. Why it is so? Because here more covalent bonds, here less covalent bonds. Here same number of covalent bonds, but oxygen takes the positive charge. It is not correct. So this is about acetate, which one? Acrolein resonance form. We have different other resonance forms also. We have other resonance forms also. Now I am taking butadiene. Butadiene. 1, 3 butadiene I am taking. How we can write structures for 1, 3 butadiene? One more example here. That is 1, 3 butadiene. See CH2 double bond CH single bond CH double bond CH2. This is the 1, 2 butadiene. 1, 3 butadiene. 1, 3 butadiene. For this we can write the structures. See whenever this bond shifted here, it will shifted to carbon. This pi electron shifted to carbon. So here CH2 single bond CH, here double bond CH single bond CH2. Here negative charge on this carbon atom, positive charge on this carbon atom. So among these two, which is more stable means this is more stable. This is more stable we can say. Why means more number of bonds, covalent bonds are more. You can count. Here 2 pi electrons, pi bonds are present. Here only 1 pi bond. So that this is less stable. This is less stable form, and this is more stable form. Due to more number of covalent bonds you can count afterwards. Then carboxylic acid if you take. Carboxylic acid I am taking R C double bond OH. One more example I am writing here. R means any alkyl group, R C double bond OH. Like this you can write. Here there are electron pairs. There are electron pairs. R C double bond OH. See, whenever this bond shifted here, this bond shifted to oxygen. So we can write R here O minus, here double bond O. See here ROOH, no? Here double bond and here hydrogen So here it will get a positive charge. So which is more stable now? This is more stable. This is more stable structure. This is less stable. You can expect now. Why it is less stable means in this structure you can observe positive charge on more electronegative atom. More electronegative atom will not take a positive charge, but it is less stable because of more electronegative atom. More electronegative En, more electronegative oxygen carries positive charge, so that it is not stable. Positive charge. That is the reason. Sometimes reasoning questions also they ask from this. Why it is not stable? Why it is stable? Why it is stable means more number of covalent bonds are present. More number of covalent bonds are present here, and more all atoms have octet structure here. Here all atoms may not have octet structure. Then lastly, I give some explanation related to bond order. So that the different examples you can go through different books for getting different examples for writing resonance structures, and after writing resonance structures you have to select order which is more stable, which is less stable, otherwise increasing order of stability or decreasing order of stability. So while reading organic chemistry, first after reading concept you have to go through the questions. You have to solve as many as questions. If you solve more questions, you can get more concept. Only by reading textbook, otherwise reference books, it is not enough to solve questions which are given in final examinations. So previous question papers, if you observe, you can get clarity about how they ask questions from organic chemistry. Organic chemistry means it is very simple only, but you have to understand basics first. After understanding basics, you have to practice more questions. If you practice more questions, you get more clarity about the concept. Okay. Then about bond order related to this resonance. Bond order. Bond order is nothing but number of bonds between two atoms. Number of bonds between bonds between two atoms in molecule. Two atoms in a given molecule. In a given molecule is nothing but bond order. So based on resonance structures, we can calculate bond order of different molecules or different molecular ions also. See here I am taking benzene C6H6. So here question is what is the bond order of benzene? Bond order in C6H6. So we can write like this: benzene structure. How many resonance structures are possible? That many resonance structures we have tried. This is one resonance structure. Then one more resonance structure is this one. There are two resonance structures. For bond order, we have this formula BO already. Bond order equal to, in chemical bonding first year we have bond order from MOD theory, molecular orbital theory. Bond order is nothing but number of bonding electrons minus number of anti-bonding electrons by 2. That is another formula. Here bond order with respect to resonance forms is number of bonds between two particular atoms. Two particular atoms. Number of, otherwise we can write it as here BO equal to total energy TOT, total number of bonds between two particular atoms in all canonical structures, all resonance structures, all canonical structures or resonance structures by total number of resonance forms, total number of canonical structures or contributing structures, total number of canonical structures. See, for benzene, I am taking these two particular atoms. Here also we should take these two particular atoms. So bond order, as per this formula, number of resonance structures or canonical structures in the denominator are 2 only. 1 plus 1, here 2. And in numerator what you have write? Total number of bonds between two particular atoms. here between these two carbon atoms one bond, between these two carbon atoms in other resonance form two bonds. So here 1 plus 2 total, otherwise sum of number of bonds between two particular atoms in all canonical structures by total number of canonical structures. So it is 3 by 2, otherwise 1.5. 1.5 is the bond order for benzene. Similarly, I give one more example. After giving this example, I conclude this session. In next session, in session 3, we will discuss about mesomeric effect. This is the third electron displacement effect or polar effect. Then hyperconjugation. There also we have more applications. So it will take I think 2 more sessions to complete all polar effects, mesomeric effect and also hyperconjugation effect. We'll discuss that in next classes. Before that, see, I'm giving one more example for bond order. So bond order in carbonate ion, that is CO3 minus 2. First of all, you should write number of resonance structures or canonical structures or contributing structures for carbonate ion. See, first I am writing that. First at the center Lewis dot structures I am writing C double bond O, here O minus, here O minus. This is one contributing structure. When this bond shifted here, it will move towards this side. So we can get one more resonance bond. Here O minus is 7 I am writing. Here double bond O, because this negative charge is shifted here. This bond moved toward this side. So here O minus. Similarly, whenever this bond shifted here, it will move toward this side. So one more structure is here oxygen, double bond C, here O minus, then here O minus. These are the 3 possible resonance forms or canonical structures for carbonate ion. So bond order for this BO equal to, so in the numerator I am writing 3. Why 3? Because 1, 2, 3. Total number of resonance structures in the denominator as per the formula. Then I am taking these 2 particular atoms. Any 2 particular, as you wish. These 2 particular atoms you can take, or these 2 particular atoms, or these 2 particular atoms also you can take. So here these 2 particular atoms I am taking here. How many bonds are present between these 2? 2. Plus between these 2, 1, plus between these two, 1. 2 plus 1 plus 1 by 3 means how much it is 4 by 3. So it is equal to 1.33 I think. So that is the bond order in carbonate ion. So this is about resonance, only resonance concept. So if you know this, if you have this knowledge to write resonance structures for different compounds, then it is easy to understand mesomeric effect, otherwise resonance effect or hyperconjugation. Okay, here I am concluding my class, my session. In next session, we will discuss about mesomeric effect and hyperconjugation with applications. So stay home, stay safe. Thank you.